My name is Filip Radenović. I come from Montenegro and I'm doing my PhD here at CTU in Prague at the institute called Center for Machine Perception. So what I will be speaking today is, I will be speaking about overview of image retrieval. Well, I will start with the standard image retrieval problems, like trying to find visually more similar images, but then I will extend my talk explaining why this might not be the most, something that users like the most. So we will be speaking about getting the new unseen information from images, like answering the questions, what or where is this, and what is interesting on the image, and so on. And at the end, I will speak about CNN image retrieval, which has a really high accuracy and a much higher speed and lower memory than standard image retrieval pipelines that were state of the art for the last 10 years. So just to be sure, when I say CNN, I don't think TV channel, I'm speaking about convolutional neural networks. However, at a machine learning meetup, this should be clear. So the standard image retrieval evaluation goes like this, like given a query image, we want to find an object that appears in that image, and we order the whole database, and then we mark the positive and negative images, and when we get to the last positive image, we count the area under the precision recall curve, and this is called MAP, the way to evaluate the image retrieval. By the way, just to say that you can stop me and asking questions anytime, because this is going to be a long talk, so maybe it's nice to be answering questions during the talk, not only at the end. So why is this not so interesting? Because getting to the last relevant image, especially nowadays when there are like billion images on internet, can be really tedious process, because the results are usually identical, and users don't, in Google Images, for example, users rarely scroll see more than few tenths of near duplicate images. So just to put a higher accent on this, I will actually show our own demo, which is working on a single machine, and it's searching in a database of 600,000 images. So it works online, so if I search for this image, I will get something like this. So what users usually do, and if you try just to memorize how it looks like, what users usually try to do is they try to search for a part of the building, for example, and they get almost the same results. I mean, the localization is correct, and it's there. However, the most similar images, even from this small cutout, are the images that are taken from the same point of view. So let's get back to the talk. Well, even though we will go beyond this, I would like first to introduce this standard image retrieval. And it's actually based on the bag of words paradigm. The offline procedure is for every image in the dataset, we extract the key points, which are basically represented as their location on an image in X and Y axis, and with an ellipse that has a scale and a shape. Then these ellipses can be various sizes. Then we normalize the ellipses into square patches of the same size, and then we use some of the descriptors to describe the content of these patches. What was commonly being used in the last maybe even more than 15 years was SIF descriptors. However, very recently, CNNs are trying to learn better descriptors that better fit this task. When we have the descriptors, they're usually low dimensional, like 128 dimensional. We create a visual vocabulary that can be orders of millions, and then we represent the image just by indices in that visual vocabulary. So we find the closest visual word, and we just remember the numbers, the indices into the visual vocabulary, and we will use that for the search. We also take the geometry, so the locations and the shape and sizes of the ellipses, and we compress them so that we actually compress them using a geometry vocabulary so that we can use them at the search time. So to try to make this more clear, if we have like a really small and simple vocabulary of 4 visual words, when a new image comes, we just count the appearances of, we classify the new descriptors, local patches, and we count the appearances of them. So this histogram of appearances will actually be the image representation. For the next image, it would look something like this. And the most important thing is that, as I said, the vocabularies are usually orders of millions, and the number of local features are few thousand. So the description, the histograms are going to be very sparse. Because they are sparse, we can use inverted file to efficiently search for the nearest neighbor. So how does it work? The pipeline looks very complicated and big, but I will come back to it many times during the talk. So hopefully close to the end of the talk, all parts are going to be clear. But this is what I described in the offline stage. So when the new image comes, we get the assignments, so only the indices to the visual vocabulary and geometries. And then in the inverted file, each visual word has the list of images that appear. So we use that to rank the images. And then when we have the short list, like we take top 1,000 images, and we use the geometries to get the affine transformation between images, or in other words, to spatially verify them, so that we are sure that they are correct images, and then we sort them based on the number of inliers, number of local features that actually helped us get the affine transformation. And in the last step, we can iterate, we can take the images that we are sure that are correct, which means that they have a really high number of inliers, and we can build up the stronger query and do the procedure again. So at the end, we get the ranked results. The posting list that was at the beginning of the pipeline works like so that when we have query visual words, so these three, we go through the posting list, which have IDs of images, and we just cast the votes to the images in the database. So at the end, when we went through all the visual words, we get the image that has the highest score, and that will be this image. This is beneficial because, as I said before, instead of having like 16, so I use visual vocabulary of 16 million, so instead of going through 60 million visual words, we'll go only to approximately like 2,000 visual words per image. So we will only visit 2,000 rows instead of 60 million rows. That's why this can be done so fast. For the geometric ranking, we use Ransack to estimate the affine transformation. And this is very important because, as I said before, this will be used to know which images can be used for query expansion. And in practice, this looks like this. So although many features might have matched between these two images, these features are geometrically consistent, and we can estimate the transformation of the bounding box, like an affine transformation, so that we can be with some certainty sure that this image is the correct image. So now that we have these images that have bounding boxes that we actually spatially verified, we take the features from inside the bounding boxes, we add them to the query image, and we repeat the procedure, and this is basically what query expansion do. So these images that will not be able to retrieve directly to the query image are actually available now. Again, in practice, this looks like this. So if we have a query image and the image that we retrieved, that's spatially verified, this is one of the images that cannot be found directly through the query image. However, it can be found through this image. So by adding its local features, because we know the affine transformation, we can just map them back to the query image, and issuing another query, we can directly get from here to here. So that would conclude like this short introduction about standard image retrieval, where we want to get the images that are most similar. And if you see so far, we always try to match these local features. So the scale of local features and the shape of ellipses plays a role there. And as I said before, because of the nature of the local features, the actual images that will be found, the first in the database, are the images taken from the same spot, even though we only search for a small part of the image. So what if the user wants to search for really small parts of the image? I will again go to the live demo and show a few examples of how that works. So for example, on the same example that I have shown before, we have, if we search now for the same cutout, but we do something that we call zoom in, or trying to answer a question, what is there? Like, let's try to see what is actually inside the bounding box. And if we rank the images based on the highest similarity, given on, actually the highest zoom in, having the same content from the inside the bounding box that we search, we get something like this. And the good thing about this is that now the image actually gives us new information, more details, and the user can do additional things with it. This can actually work in an opposite direction as well. So if we have a cutout from a building like this, and we, for some reason, cannot remember where is this, or we would like to know, we can do a zoom out. And in the reverse procedure, we will actually get the building where this object appears on, and we will get its localization. If we are still not sure what this is, we can do additional zoom out, and we can actually get the full building. So, okay, this is just in the case that internet is too bad for the demo. So what changed? I mean, we still use the same pipeline. We use the same local features. However, we take advantage of their scale now to actually be able to push the search towards zoom in or zoom out. So what do we change now? On the first ranking of the posting lists, we actually don't just cast votes one by one. We weight the votes because we know the scale of the local features. So if we know that we want to find a zoomed in image, we will actually cast a higher votes towards zoom in local features. I mean, a higher scale local features. And then when we have the affine transformation, we have these rectangles that I have shown you, and we can actually estimate the area inside the rectangle as the number of pixels, so we can know exactly what's the size of the zoom in. So we can rank the images based on the zoom in rather than number of inliers, and we can get the output that are zoomed in images. Also, the query expansion is really important because now we take these first ranked images that are the highest zoom in, and we already zoom in the zoomed in images so that we can actually get much higher zoom ins. And in few iterations, you can get really remarkable things with this. For zoom out, the procedure is the same. Only difference is in the ranking, where we don't push towards zoom in, we actually push towards zoom out. So with same local features, we'll cast higher votes in the smaller scale local features. So because of this method, like going through the database, we can actually be able to match this cutout from original image to something from here. So how many people does actually believe this is the correct thing? You can raise hands. We can make it really fast. Okay, the second image, third, and fourth. Okay, so it felt like the fourth had most votes, but I'm not sure. Okay, so I will show it gradually. So actually the cutout is from Prague, from Old Town Square, Týnský chrám. And this is the original image. So this is how the computer sees it. But with gradual steps, so like this is one step, and then in the query expansion we can get additional step, we get to this. So whoever said third, that was correct. For these extreme zoom-ins, like this example that I have shown, we only rely on few local features. So for this example, we actually, from the original image, we got to this image. And then from this image, there is only 3 features. The blue ones are the ones that are actually verified, and the yellow one is the one that matched, but was geometrically not consistent. And the second image that helped us was this. So it was only like 6 features that helped us get this, because we reduced the number of features that we trust to make the decision. Zoom in and zoom out have much bigger rate of mistakes than standard image retrieval. For this example, I would actually like to show it live again. Well, actually for the one that I have shown, if you don't believe me, we can do it live again. And just doing zoom in would get us this. Now for the zoom out, I was showing a part of the building being zoomed out, but what we can also do is we can zoom out the whole building. So the results will be something like this. Although this looks like it might be a mistake, it's not, because this, even though being like a photograph on the wall, this is still zoomed out. It's in a smaller resolution than the original image. But what we wanted is probably this, and we can do iteratively. One more step, we will get something like this. And then we can do one more step, and we get the view from Eiffel Tower to Notre Dame. So again, this might look like it's wrong, but because I've seen these images so many times, I'm sure this is correct. However, it's hard to convince you, and this is the second image. Is you can see that it's correct, because I don't know if it's visible on the projector. I will try to zoom in a bit. So here is this Hotel des Invalides from Paris, and the first image where you can actually see Notre Dame barely is here, and Notre Dame is here. So I will try now to zoom in back from, okay. Or additionally, instead of zooming in into full Notre Dame, I will maybe just try to get these sculptures here. And we can get results like this. Okay, so this is the example I have shown live. So just to summarize, we basically don't get directly the zoom-ins or these extreme zoom-ins and zoom-outs, because it's impossible. There is just not enough information to match these images. However, by doing cleverly and fast a path through the dataset, if you do it iteratively and slowly, eventually you can get these extreme zoom-ins. So one more question that we try to answer is what is interesting on this image. So if a user comes and takes a photograph of astronomical clock on the Old Town Square, what would be interesting? Where should he look? So we managed to make a map like this, which the red areas are the areas that were photographed with the highest zoom in comparing to the query image. So basically, we can show to the user based on the zoom-ins in the database. So we find everything that's extremely zoom-in in the database. We assume that this is interesting because somebody actually took an effort to zoom in into these parts. And then we show user exactly where they can look to find interesting parts. Additionally, these images can be easily matched with images from Wikipedia, and then there could be some textual description, so for an interesting tourist guide application. The other criteria could be, where should I look? Like, what's interesting based on the frequency of images that appear in the database. So if the detail is really small, of this size, comparing to the query image, then these are the parts where most of the people took photographs, and as the details get bigger, you get more area that's red. Somehow naturally, the top of the building appears only at the bigger size of the window because this is far away and this is not that easy to crop when photographing, so that's why there are not so many details of this part like comparing to the parts closer to the ground. So for this particular query, the most important thing, so we run like a normal zoom-in query, and the most important thing is the query expansion. So here we do some more work. When we get the zoom in, we get like just slightly zoomed in images, as many as we can find in the database, and then we group them based on their based on the area that they are depicting. So we create n groups, and then for each group we run the geometric consistency test with the local features, just to be sure that all images will be from the same building as the query image, so that we don't drift onto some other areas. And then for each of the groups we issue a new expanded query, and then we can get the results that I have shown. Okay, so this, okay. Okay, so like this would work with any. We personally, and this demo that I'm showing, we use hash and affine features. That's why they are ellipses with so they are actually multi-scale hash and affine, which means that affine shape is memorized in the shape of the ellipses, and we have the scale of the ellipses for the multi-scale search. But you can use different things like dog or Harris multi-scale, stuff like that. So I think that for many years, hash and affine was something that worked best in image retrieval. Okay, so I will be moving to image retrieval in 3D reconstruction. If there are some other questions for the previous area, you can ask now, or we can get back to it later. Okay, so I move on. So for the 3D reconstruction, on the large scale, what people did, first thing that was done is just taking all images and trying to do pairwise matching, so try to get matches between all pairs of images. This will actually give a really nice 3D reconstruction in a high detail. However, you can do only this with few tens of thousand images, even with the strongest machines now. As you go into million or billion images, it is just something you cannot do anymore. So what 3D community started doing is, instead of matching all pairs, they just do the matching through standard image retrieval. So for each image in the database, they run a really fast query to get the short list, and then they use this to build a 3D reconstruction. This is very efficient, and it can scale up to millions of images. However, because they use the standard image retrieval, I already have shown what are the problems with it. You will usually get the near duplicate images, and then in the big databases, you will not get the details, you will just get the generic view of the building. What we propose is, instead of using only visually similar search, we propose using zoom in, zoom out, the things that I have shown so far, and additional new thing which we call sideways scroll, where we actually try to get images with a significant viewpoint change so that we can build up the more context around the query image. So starting from this query, what sideways is trying to do is we try to get right from the query and left from the query. So this is a perfect example, because left there are buildings, so you just move normally left. To the right there is nothing, so we actually go around the corner and we get the view of the building around the corner. For the symmetric images, this proposes a new challenge because the building actually looks almost the same from the other side. But because we are using these details that I was speaking before, we will be able to disambiguate between this side and this side just by matching the small details that differ. So again, same pipeline. I'm trying to explain now how sideways scroll works. So for it, it's the most important, again, to use the geometry, but in this case, we don't use scale. We use the position, x and y, of the points that we verified with the query image. So we basically, if we want to go left, we will just take, in the retrieved images, we will just take the point left from the query that are not visible in the query. We add that in the query expansion. We build a query expansion from like top 10, 20 images, and we run again the query with only left local features so that we get moving to the left, or if we want going to the right, we just take right local features. In practice, this looks like this. So this is a query image. We want to move to the left. This is one of the retrieved images that actually reveals more information to the left. So we take that as a new query, but we discard all the features that were matched with the original query, and we use only the ones that are on the left, and we will get something like this in the retrieved results. If this is repeated enough times iteratively, we can actually make a full circle around an object like this, or in the case of Old Town Square, we get the full circle around the square. So just to summarize, we use visually most similar just to build up the near duplicate images, because this is also important for the 3D reconstruction, but we need more. So we get zoom in and details to actually get to the details like this, which are represented in only few pixels in the query image. We get zoom out to get as far away as possible to get a higher context, and sideways to the left or to the right to get, again, more context around the query object. So now I will show the video of 3D reconstructions. Well, basically, the idea was take a single query image like this and reconstruct as much as you can with a 3D reconstruction. So I assume that you know that this is Old Town Square in Prague, and the query image was taken from here, looking only at this corner. And with all these queries that I was speaking about, starting with only one query and having a really big database in the background, we managed to make a full circle and to reconstruct the full Old Town Square. For example, Tinský Chrám was not visible at all in the query image, and it's reconstructed in a lot of detail. The red color here on the heat map shows the amount of detail that we have. So more red means that we have these local features reconstructed very close to each other, while cold or blue means that we could get more details there. So what we actually use is we iteratively search for the parts that were blue and to try to reconstruct all the parts as much as possible. Okay, so what I would like to show. Okay, so for arc, as I said, it's challenging because from all sides there are some things that just repeat, and this confuses local features. So as you can see here, we actually managed to make a full circle around the Arc de Triomphe, and we got from zoom outs, we got images from the street, and we started somewhere from here. We actually tested this, and we know that if we start from the other side, we will get almost the same 3D reconstruction. So it doesn't matter from where we start, as long as we can make, as we can connect the images, we will actually get the full reconstruction. And at the end of this particular object, I will just show how much details we actually do manage to reconstruct. Okay, so although this is a point cloud, we don't do reconstruction of textures. These are just points from images. It's a dense point cloud. We managed to get something like this, and this is an image for the reference. After this, we're thinking, okay, now we have these really nice sparse 3D models, point clouds. Let's try to reconstruct the dense model, so like texture. And what we notice is that because we gradually do retrieval iteration by iteration, we actually managed to match all these images into the same model. So starting from a day, we have gradual, we can match these two images, but maybe we cannot match this one directly with this one. However, gradually, when we go through all images, we actually get from day to night. And this can be problematic for the dense reconstruction. So when we use the standard pipelines for the dense reconstruction, just run them on our data, For example, in Moulin Rouge, this is what you get. And there is a lot of artifacts that appear because this building looks completely different during day and during night. To zoom it a bit, this is how it looks. So what we propose is, in order to avoid the artifacts that appear everywhere around the standard dense reconstruction, we propose to take advantage of the nature of local features to actually be matching more with the same modality, and to split this point cloud into day and night and do separate reconstruction for the day and separate for the night. Although this works for some landmarks like Moulin Rouge out of the box, for others like Vatican, you get really bad night model because some parts are just not illuminated during the day and they are really nicely visible during, they are not illuminated during the night, sorry, and they are really nicely visible during the day. So what we propose to do here is to fuse the geometries. We know that the structure shouldn't change. No matter that it's day or night, the structure should stay the same. So we fuse the day and night, and then we can recolor the fused geometry with any color we want. We can learn the color transformation from the parts that are visible during both day and night. So instead of this, we can actually get much fuller model of this cathedral during night. Again, I would like to show the video with more examples. Okay, so as you can see, the day reconstruction looks much better, and many parts were not visible during the night. So we just used the simple color transform, where we, as I said, took the parts that are visible both in day and night, and we just transformed the color from day to night to recolor the night parts. Although in most of the cases, the night model is the one that benefits more, sometimes this thing helps even the day model. So for example, on these commercials like Coca-Cola sign and stuff like that, during the day, the advertisement, if it's lit during the night, during the day it will not be visible, especially if it has some grid structure. However, during the night, if it's well lit, we can reconstruct that and then we can recolor it at the daytime. So there are a few examples where this helps at day reconstructions, but mostly the help comes to the night models. Yes. Okay, so for this thing that I'm showing now, we actually crawled images from Flickr, and we had like 7.5 million images. And then we start with a single image, and we, in all these 7.5 million images, we don't know which ones are correct. So we try to find those. And for the largest models, it's like 10 or 15,000 images. This is how many of them is there in these 7.5 million images. But there are some models that only have like few hundreds or 1,000 images. That's also enough to have a really nice 3D reconstruction. Of course, the more images, the better. But we reconstructed something like 1,000 different objects from this model, and some of them have like 100 images, some of them have tens of thousands. Are there any more questions so far? Okay, so I move on to the last part of the talk. So all these things that I was showing, this was something where people were taking advantage of the geometry of images, something that people worked on for maybe 20 years, and people know what works well and how to utilize this in the image retrieval. And then very recently, people started using CNN image retrieval. CNN image retrieval is very popular because the description of images that we actually use is not anymore like this 16 million histogram of appearances. It's usually very compact, like 256 dimensions or 2000 dimensions, depending on the architecture of the CNN. And so, because it's so compact, we can store them. We can store many of them in the working memory, and we can use fast nearest neighbor algorithms to search through them because they're very short codes. So Basically, when we started working on it, we tried to utilize the knowledge that we have from bag of words to train the CNN. So to solve the significant viewpoint and scale change, what bag of words used was affine local features like Hessian affine that I mentioned before, and invariant descriptors like SIFT. While in CNN, you basically need lots of training examples for the significant illumination change. You do color normalization before the description of features. CNN, again, lots of training examples. For the severe occlusions, use the locality. Local features are really small, so you can actually find the object that occupies a really small percentage of the image. Again, for CNNs to do this, you need lots of training examples. And at the end, what you don't want is, you don't want to get visually similar but different objects. Or if you want to get them, you want them to be behind the actual object that you search for in the ranking list. So bag of words does this with the discriminability of the features and geometric verification. CNN, guess what? Lots of training examples. So I was trying to push this lots of training examples as a strong motif here, because this is not always very easy to do. You have large internet photo collection, like in our case it's 7.5 million images, and you want to train a CNN. So in order to do this, you need to have image annotations. For the bag of words, we just build a vocabulary, which is unsupervised. You input only one parameter saying how many of visual words you want. While here, you need to have a really strong annotations. So what people have done is they used mechanical Turk, which you have to pay, and it's not very accurate. What some other people have done is manual cleaning, so researchers sitting in front of the computer and just clicking on images, which is a really expensive waste of researcher time. What we propose is to do this in an automatic way, very accurately, and it comes for free. So before I go into how we do it, I would just go shortly into the recent history of CNN for image retrieval. So what people first try to do is they use a network that's pre-trained for classification, which is a different task than image retrieval, but it's close enough, and they try to pull the descriptors from there and to match images, and this worked well. However, not so well, because, for example, if you look what was used for classification to train, this was all used to be a building class for the network to see this as the same class, while in image retrieval these will be all different objects. Then there were new methods that use the textual queries to download images from the internet and then use this as classes to train. And these are all images from the same building. Although, yes, they are from the same building, they sometimes look at completely different size, or they are indoor or stuff like that, so that they are actually not so accurate and so good for learning the CNN. One of the very recent approaches, NetFlood, takes data with GPS, and they try to utilize this GPS in the training procedure. So they have some annotation, they call it weakly supervised fine-tuning. However, again, if we have GPS, this is only the location, we have no idea where the cameras are looking. So the images that are very close can be looking at arbitrarily different things. So these images are positive instead of these. And they had to deal with this during the training time. They had to solve this somehow. We propose creating pairs of hard positive and hard negative images, and we propose using what we have done before. So we propose using the 3D reconstructions to actually get very accurate image pairs. And we can do that because with these very detailed 3D reconstructions, we know the camera orientation and we know the number of inliers. So for each pair of images, we actually know exactly if these are positive images and how close they are, so that we can push the algorithm to learn even the harder examples. So for example, for negative images, what you can do is, if we take these images as queries, we just want to find the image that's the most similar to the query image, but it's not in the same 3D reconstruction. So this is how it will look. And usually in metric learning, it's very common to use more negative examples because there is much more negative examples than positives. If you would try to do that in the same procedure, so taking additional closest images that are from a same 3D cluster, what you will what will happen in most of the cases is that near duplicates to the to the most similar negative image will actually be also very hard negative image, and you don't want that because it's redundant. So what we propose is to take one image per 3D cluster. So we take hardest images from different clusters, but one per cluster. For the positive images, in the case where they had GPS coordinates, like in NetVLAD, what they can do is they take the current closest image by the CNN, and this is usually good, but the problem is that this image is already found as positive by the CNN, so the CNN will not learn much from it. What we propose is, again, using bag of words or the number of inliers in the 3D reconstructions, or to make it even harder, we take random images from the top K closest images based on the bag of words procedure. So now we can get images as hard as these to push the network to learn more. Comparing to the bag of words pipeline, this is actually the pipeline that you use to process the images. So for a given image, you pass it through convolutional layers, and in the last convolutional layer, you just do pooling. In the simplest thing you can do, and what we use is just do maximum pooling per channel, and then you get an L2 normalization, and you get d-dimensional descriptor for each image. As I said before, for AlexNet, for example, this is 256. For VGG, this is 512. For ESNet, 2000. We do L2 normalization because then after that you can easily find the nearest neighbor just by using a dot product between images. So for the at the training time, as I said, we have pairs. So we have a query image and its positive image. We run them to get the descriptors, and then we use the contrastive loss to learn both branches at the same time equally. So basically, if it's a matching pair, then we penalize the network if the pair, if the positive pair is not close enough, and for negative pair, we penalize the network if the pair is not far away enough. We also try using triplet loss, but in our experiments, contrastive loss worked much better. So triplet loss basically just optimizes in 3 branches, so at the same time observing query, positive and negative image. The pooling method that I was speaking about, so when you pass an image through the network, this is the activations that you get in the last convolutional layer. Again, the big K, for example, for AlexNet is 256, so you get 256 of maps like this, of activations. And for max pooling, you just take the maximum activation for each one of them, and you get a 256 dimensional descriptor. Or for sum pooling, you just do an average over the whole activation, and you get your descriptor. Well, in a very recent work that's still not published yet, we use also generalized mean pooling, where we do generalized mean per convolution activation. And this P parameter can be learned by the network. So we actually put it inside the backpropagation to let the network learn it. And if the network decides, it can be really high so that it emulates maximum pooling, or very low so that it emulates some pooling. In our experiments, P usually stayed around in between 2 and 3. So this is what network learned for most of the architectures. As the last step after the training, we do whitening and dimensionality reduction. So this is something that was also known from bag of words image retrieval. So these image representations were whitened. And what does actually whitening do? So first, because we have only positive data, you want to move the center. So you do the centering, or just subtracting the mean to move the center in the center of the data, which comes useful because then the negative evidence or 2 representations having zeros at the same places will actually give positive vote, which means that we don't only count where the images have the same values, we also count where they don't have a value. Then we rotate the data to remove the least informative dimension, so that we can do the dimensionality reduction without any loss, without small losses in performance. And at the end, whitening, we just transform the data, we whiten it, and this was shown again in like 5 years ago to addresses overcounting, or this suppresses the features on images that appear a lot at the same time. So for example, 2 images of the building, they usually have a lot of features appearing on the windows, and this is not probably something that's very informative because all buildings have a lot of windows, so we want to suppress that and to have more discriminative features to give higher scores. The whitening thing can be learned as a post-processing stage using the PCA. What we propose is, so PCA is unsupervised, you just need independent set of descriptors and you can learn it without any labels. Because we have labels, we use linear discriminant projections to learn this, and also we tried learning it in end-to-end. So whitening layer can be added just as a fully connected layer that will do the transformation, and optionally it can do dimensionality reduction. However, this was shown to slow down the convergence and usually be only as good as, at most as good as the method 2. So given that it was slower and it was never better, we just stick to the really fast post-processing and learning whitening in a supervised way with the training data we generate. At the end, I'll just go through the results. So we used standard image retrieval results like Oxford, Paris, and holidays. That Oxford and Paris contain landmarks from Oxford and Paris. Holidays contain some landmarks, but also some generic scenes like beach, sea, stuff like that. And we used a 100K destructor dataset. All these datasets are labeled so that we can actually measure the performance. And very important thing is that we never seen any of these buildings or objects during the training. We manually, if any of them were contained in our training dataset, we manually remove them so that we can evaluate if we generalize actually to unseen objects. So all the things that I was speaking now, one by one, they actually getting harder negatives and harder positives. This actually helps the performance, and our learned whitening gives additional boost. The most, the very interesting experiment is comparing the teacher or the bag of word method that I was actually showing in the demo that we use to learn. We use it to learn our CNN, so we actually compare how this 16 million image representation compared to a really dense. So this is very sparse, so the search is actually really fast. However, this being much lower in memory and much faster, the results are almost there. After adding the generalized mean pooling instead of max pooling, we actually outperform teacher on all datasets, and after adding a query expansion, that in this case is just simple mean average, like aggregating the descriptors of the top 10, let's say, ranked images, and then issuing a new query, we get really high scores that outperform the bag of words on all datasets. Unfortunately, not everything is amazing, because for really small objects like Apple logo that appears in really small percentage of the image, so for example in this case it's in this small corner, local features really still do a really amazing job. So the first incorrect image was at 128 rank, and when you use CNN you get completely confused, and our method didn't manage to find any. These are like top almost 10 retrieved results. However, there is a new publication where they tried to use regional pooling to actually and diffusion to actually search for these small objects, and they managed to do a really good job. The next problem is, for example, this. So everybody knows what this is. For local features, this is super easy to get. This is a painting that exists in our dataset many times. So again, the first incorrect is after 159th rank. However, when we use CNN, we do get some good images, but we still get faces. And this is probably because we actually use the network that was, to initialize our learning, we use the network that was trained on classification. So this network was trained to find a face as a class, and we only learned on landmarks, so we never taught the network to actually be searching for a specific painting, or in this case, person. So fine-tuning might not be enough, and hopefully we will actually do training from scratch to see if this will give better benefits in these specific cases. So do I still have time to go through? Okay, so this will be short. So now, after we did CNN image retrieval, we actually try to tackle the more complicated area of sketch-based image retrieval. where basically, okay, it's a bit hard to see, but these are just sketches drawn. And using these sketches, we try to find, we search only among images. We try to find images. To tackle this, recently people spend like practically years of man hours to create data set of sketches to train them. And we try to reuse the things that we did for CNN image retrieval and not use any sketches. So we actually try to generate a lot of training examples without to teach the CNN to find the sketch, to retrieve the sketches without ever seeing a sketch at the training time. So how we did it, like if we have images like these, just random images, and you extract an edge map, it looks something like this, and this is usually not something that looks like a sketch. However, we added a specific block at the beginning of deep network. That's a simple differentiable function that has 3 parameters, p, beta, and tau. And we let the network learn these parameters to make a transformation like this, to actually filter the edge maps so that they look more like sketches. After this filtering, after we let the network decide by itself how to learn this filtering, this is how our filtered images look like, and these are how sketches look like. So now you have to admit they look much closer to actually what we want. So again, I'm repeating, we use the same data set that I was speaking before, only landmarks, to train the CNN. So we never seen any sketches at the train time, and then we try to test it at the test time. So for example, for training, these are the positive pairs that we used, and these are the negative pairs, so only filtered edge maps. And we achieved really high performance on the sketch retrieval, but as a side product, as a really nice side product, we actually get some benefits in the standard image retrieval. So if you try to search, like this is the Bridge of Sighs, the bridge in Oxford, if you try to search it by using a painting of this image, the CNN that I have shown before that works on RGB images will fail completely, because the colors completely change, so it doesn't see it anymore as the same object. However, when we extract the edges, so if we only preserve the shape, we manage to get a really nice retrieval of the same bridge. The second case is super dark images, so images that are very dark, CNN completely fails. However, because after the edge map and edge filtering, the shape survived, we managed to retrieve images really nice. Okay, so this somehow slowly concludes my talk, just to outline what I was speaking so far. I first spoke about standard image retrieval, that although very important, might not be the most interesting thing for the users. So we went beyond similarity retrieval. We tried to get new unseen information, extreme zoom-ins and zoom-outs. So actually saying what or where is this, and what is interesting, where should I look? And at the end, we used all this knowledge that we have from the last 10 years and image geometry used in image retrieval to guide the training of the CNN, and to get CNNs that are really good at image retrieval with high accuracy, high speed, and low memory without using humans in the loop ever. So no human supervision, completely automatic training, and getting really nice results at the end. That will be it. Thank you, and all questions are welcome.
So, any questions? Or everybody is okay?
My question is about when you are training CNNs, have you think about like zooming in, zoom in, and zoom out as well, or have you done some region proposals there, or not at all?
So we have done region proposals. However, we didn't train with them, but there is a concurrent work actually published at the same conference as us that trained it with regional proposals, and they achieved a bit stronger results. However, the generalized mean pooling somehow implicitly learns where it should fire on which regions, and also it has been shown that on residual networks, ResNet, because they are much deeper and much more powerful, these proposals in the sense of regions don't help so much anymore. And the paper that I said that specifically guides the diffusion of regions using our network managed to get smaller objects. But all this that I have said now was only done to get the small objects, in the sense that they occupy the small percentage of the image. We didn't specifically tackle zoom in and zoom out with CNN, and this is something that we hopefully plan to do in the future.
Just a small question, are those papers going to be for the CVPR in the summer or some other conference?
So our original paper on CNN was ECCV 2016. The paper with regions and diffusion was CVPR 2017. It's already online, but it will be presented in CVPR, which is in maybe a month. And I think there are on archive even more papers now online, like incremental work after that.
So more questions?
You said you use affine transformations in the classical, like in the reconstruction and so on, but does your method also work for, say, small objects like statues? Because if you are, because I think the transformations are not affine in general. If you consider different focal length and so on, so does it work also for small objects?
Okay, so it actually, so the affine transformation will work on planar objects perfectly. If they are not planar, then they should be roughly planar. So even sculptures, somehow, if you see only one side, you can see it as roughly planar. It's not perfect, but it will work. And I think there are better methods to do the geometric consistency on objects like this. However, doing a affine transformation is really fast. You can do it for 1,000 image pairs in like 1 or 2 seconds. So this is main reasons like efficiency, and it works reasonably well.